Greetings and welcome. Subscribe the channel Thermal Engineering for video sessions. This is video session on LMTD for counterflow heat exchanger. In this session you will be able to explain LMTD means log mean temperature difference for counterflow heat exchanger. Now the question is why LMTD is required in heat exchanger analysis. So in heat exchanger there is a heat exchange takes place between the hot fluid and cold fluid. So there is the temperature difference between the two fluids which is continuously changing from the inlet to the outlet of the heat exchanger. This temperature difference must be averaged over the entire length of a heat exchanger. So LMTD means log mean temperature difference helps in determining the size and rate of heat transfer in heat exchangers. For this, here are some assumptions. The overall heat transfer coefficient is uniform through the heat exchanger. The specific heats of fluids are constant and the potential and kinetic energy changes are negligible. Mainly there are two types of LMTD. LMTD for parallel flow heat exchanger and LMTD for counterflow heat exchanger. In this video session we will see LMTD for counterflow heat exchangers. So for counterflow heat exchanger, here is the flow arrangement and temperature distribution. This is a single pass counterflow heat exchanger. So in this case consider an elementary area dA for this length dx. So heat transfer through this elementary area will be dq, that is equal to U into dA into delta T. U is overall heat transfer coefficient, dA elementary area, and delta T is the local temperature difference. See here, this is a hot line and this is a cold line. So here this temperature on hot line is a TH and on cold line TC. So this difference is a delta T. Now here other temperatures are TH1 and TH2. These are the inlet and outlet temperature of hot fluid. In this case this is moving in forward direction and cold fluid is moving in counter direction or opposite direction. That's why here inlet temperature is TC1 and outlet temperature is TC2 here, and this is the flow direction. Now for the analysis, now we will have here energy balance equation for the element heat transfer. dq is equal to minus mh into cph into dth is equal to minus mc into cpc into dtc. Here m means mass, cp is specific heat, and dt is a temperature difference. H hot fluid and c suffix is cold fluid. Here the negative sign because both the fluids are moving in the direction where the temperature of fluid is decreasing in the direction of heat exchanger length in counterflow arrangement. Now here if you see this dTh will be on this hot line. Temperature difference during this elementary area for length dx, and dTc is a temperature difference on a cold line during this elementary area flow. So we will have here the further modification in the equation. See here, for the product of MH into CPH, we can take together it as a CH, means heat capacity for hot fluid. Similarly, for product of cold fluid, this will be CC, means heat capacity of cold fluid. So here CH into DTH and CC into DTC. Now we will have the two equations. For DTH is equal to minus dq upon CH, and for DTC is equal to minus dq upon CC. Now the temperature difference already we have discussed. DTH minus DTC will be d of delta T. Now already we have these DTC and DTH and DTC expressions. We have equation 2 and 3. So we will substitute these expressions in this equation number 4 at this place. So equation will be what? D of delta T is equal to minus dq upon CH, and here that minus sign is here, and also there is minus sign for this DTC. So these both minus signs will become plus sign. So that's why a plus sign have been come here. Okay, so now here we will take dq as a common, minus dq as a common. So inside the bracket 1 upon CH, and here will be 1 minus 1 upon CC. Now putting dq is equal to u into dA into delta T. This is the basic formula. This we will put at this place. So above equation will be what? D of delta T is equal to minus u dA delta T into this bracket. Now this delta T we will bring on the left side. So here it will come at the denominator, and right side remaining terms. This we have done for the integration purpose. So integrating above equation between the limits 1 and 2. 1 is the inlet, 2 is the outlet along the heat exchanger length. So integration of left side, here the lower limit is delta T1, upper limit is delta T2. Right side minus u and this bracket, all these are constant terms, so remain outside of the integration side. So integration of 1 to 2 will be what? Of dA. Now integration of this term will be what? 1 upon something, means log of something in the mathematics. So here natural log of delta T2 upon delta T1. These are the limits what we have put in the integration output, is equal to minus UA into this bracket. Integration of dA came here A. So this will be the equation number say 5. Now we know that total heat rate between two fluids is Q, means capital Q, is equal to CH, means heat capacity of hot fluid, into temperature difference on hot line. See here in the diagram, on hot line TH1 and this is TH2. So this is the temperature difference. For cold line temperature difference TC2, this temperature inlet and this temperature outlet TC2 minus TC1. Now we will arrange this equation in this way. So we will get these two equations. One will be for 1 upon CH is equal to 1 upon Q into TH1 minus TH2. Say equation number 6. And other equation 1 upon CC is equal to 1 upon Q into TC2 minus TC1. Say equation number 7. Now see equation number 5. Here 1 upon CH and 1 upon CC. For these two terms we have these equation 6 and equation 7. So substitute these expressions in the equation 5. So here left side natural log of delta T2 upon delta T1 is equal to this minus UA, and then in the bracket here square bracket For 1 upon Ch, write this expression, means this 1 upon Q into Th1 minus Th2. Then minus sign. Then for 1 upon Cc, write this expression here. So 1 upon Q into Tc2 minus Tc1. Complete the bracket. Then taking 1 upon Q outside of the bracket will come here. Inside the bracket, here we will have the arrangement, that is Th1 minus this Tc2 and minus another bracket Th2 minus this Tc1. Now why we did this? So here Th1 minus Tc2, if you see here at the inlet Th1 minus this Tc2, so this is a temperature difference at the inlet, means we can write for this delta T1. See here in this diagram. Similarly, at the outlet you can see this is a Th2, means exit temperature of hot fluid, and this is inlet temperature of cold fluid, because this is the counterflow arrangement. So this is the exit of hot fluid, this is the inlet of cold fluid. So this difference Th2 minus Tc1, which is here. So this is what actually delta T2. So in the further slide for these two brackets, here what will come? That we will see. Here what comes? Delta T1, and here delta T2. Now this minus sign we will take inside. So what will happen? Here ln of delta T2 upon delta T1 is equal to UA by Q. Inside the bracket, here sign of these terms will be changing. So delta T2 will become positive, delta T1 will become negative. Now writing this equation in the form of Q will be equal to what? UA into delta T2 minus delta T1 divided by this term, that is natural log of delta T2 upon delta T1. This equation can be written in this way also, means subtraction of 1 minus 2. This is a subtraction of 2 minus 1. So here is a ratio of 2 to 1. Here for the subtraction between 1 and 2, here will be ratio for 1 and 2, delta T1 upon delta T2. Now comparing these equations with equation Q is equal to UA delta Tm, we will have for delta Tm either this equation or this right side. So we can write here delta T1 minus delta T2 upon natural log of delta T1 upon delta T2. Now this is the equation for what? Delta Tm, means what? Log mean temperature difference. Now this is for counterflow arrangement of the heat exchanger. So at the end of this session you have studied and you can explain log mean temperature difference for counterflow heat exchanger. So subscribe the channel Thermal Engineering for video sessions. Thank you.